Let me share my screen.
Okay, okay, sir.
Is it visible?
Yes, sir. It is visible.
Okay, perfect. So let me welcome the participants and all who was working with this particular event. And I would be introducing about one of the novel technologies. You can say it as an advancement in the construction technology or construction systems, what we are using. So this is a part of those kind of advancements. So let me go with the some brief introduction about what we know and how this is helpful and what are the practical aspects, theoretical aspects. I would not be dealing with the equations, but the mainly the conceptual part of the technology. So before going with this technology, let us go back to the RCC fundamentals, what we have presently in our fundamental textbooks. So this is the first example, probably the first example we generally would be taught while we are into either applied mechanics or maybe stress analysis or structural analysis. So this would be the first example in brief actually. So wherein we like to study the simple bending actions in RCCB with the help of this kind of example. So this is the simple supported beam. There are two supports and a beam is resting on those two supports, and the beam is having some load on top of that particular beam. So what are the internal stresses or internal actions that are created or that are generated because of this kind of system is nothing but you can see that there will be compression at the top and tension at the bottom when we are dealing with the mid-span portion of this particular element. We call it as a beam. And we generally denote this kind of internal actions or internal stresses with this kind of diagrams, like where you have a triangular diagram. There is a vertex, and then you will have a maximum compression at the top, and there will be then it will try to minimize, and then there will be neutral axis, and then again you will get a maximum tension at the bottom. So this is what we learned in RCC fundamentals. So we and based on this actually we try to give the material based on this kind of internal actions. So wherever the compression prevails, the concrete is good enough to take care of that compression, so we keep the compression concrete in the compression zone. Whereas in tension zone, the concrete is not good enough to take care of the compressive or tensile stresses. So what we do is we provide the reinforcement either in the form of mild steel or HYSD or TMT, etc. So this is what we do in case of our reinforced concrete members, RC members. So going beyond this, there is the next step that is known as pre-stressing. You must be knowing about the pre-stressing, but here we'll be dealing with another kind of pre-stressing systems that is you can say it's quite new in India. It's not new in across the world, but for India it is a new technology. So let us go in brief of pre-stressing. What is the meaning of the pre-stressing? In pre-stressing, actually, we are stressing the member. We are introducing the internal stresses in the member such that that gets balanced when actually the internal stresses due to the external loads, that is service loads, is coming on that particular member. So we are actually inducing this before the member is subjected to design loads. So that is what is the meaning of pre-stressing. This pre-stressing is generally being applied with the help of a flexible cable. So there are several names of that cable. Either you call it as a tendon, it is cable, or it is a strand, or it is a wire. So these are the mechanisms. These are the different names, and you can say different, but the mechanism is same for all. So in design, actually, what we are doing is we are trying to manage the stresses. Stresses means the internal stresses in the member, such that we can minimize the stresses. We can balance the stresses. Whether there is a tension stresses are generated, so we are trying to introduce the compressive stresses over there in that zone, so that tension and compression both can nullify each other, and we can minimize the overall resultant stresses. Similarly, on the other side, like when the compressive stresses are there, we can, if we can introduce a little bit tensile stresses over there, again there will be you can say a reduction in the stresses, and this is how we can manage the stresses with the help of pre-stressing. This has been developed, or this has been thought of by and actually discussed by Professor Gustav Magnell, and he actually tried with this kind of example, when you have a, suppose you have a rack of books are being laid on the rack, and if there is no rack, what will happen is book will not be at its position, right? So without rack, if you want to get the books intact, in its position, so there is another way that is known as apply enough precompression force so that it can hold. So you can see here in the diagram, by this example, he was able to explain this technology of, and in this very, you can say, vital element that is known as precompression for this pre-stressing system. The other nut and bolt of this pre-stressing system is being developed, and it's been discussed by Professor T. Weiling. He's a structural engineer actually, and you can see here, this is a two-span beam, one support two, support three. This is a beam, and if the cable is laid straight, you will get a certain P by A, or pre-compression. But if you lay your cable in certain profile like this, you will have a mid depth profile here. You will have a bottom profile here. Here you will have a top profile like that. And with the help of this kind of profile, additional advantages are actually being generated, and that is known as load balancing or weight balancing aspects of this pre-stressing system. So with this, actually, we are getting the pre-compression, that is balancing the stresses, and by load balancing also, we are getting more towards the balancing the stresses, as well as we are getting you can say upward force, upward thrust in the member that can balance the gravity forces which acts downward. So this is how, with this, actually we are working against gravity, and we can reduce the deflection in the beams and slabs with this concept. So with this, both the pre-compression and load balancing concepts are being discussed here. You can see, graphically, this is the pre-compression P by A. This is the example. And for this load balancing, this is the diagram, or you can say stress diagram, that is being actually, generated in the midspan of this beam, when, your cable is having, this kind of blue color profile. That is, you can say it is a reverse parabola. Let us again go back to one of the learning experiments we must have in our either theory of structures lab or structural analysis lab. Something like this, there are two pulleys, you can say frictionless pulleys are there, and there is a string or cable, and at the end of the string, there is a weight, you can say, at the or both the ends, you will have a weight. So by virtue of this weight, what will happen is, there will be force in the cable, and that is of tension nature, right? And due to that tensile force in the cable, the string or cable will remain straight. If there is no force, then cable will sag because of its self weight and gravity. So here, we'll try to play with this something more. So if we have a transverse force acting on this cable, what will happen to the cable is something like this, right? The cable will try to sag based on the force, the amount of force and the type of force. So we call this as a deflection in our member, whether it is a flexor member. So it's that, for example, it's a slab or beam. So we are, simulating both the things, the theory as well as, the applications of that. So here, to reduce the sag, or you can say to minimize the reflection of this particular element, in presence of the vertical downward force, what we need is, we need a balancing force required, right? So how to get that balancing force? One of the way is by applying some more force at the end of the cable, or you can say by increasing the force in the internal action of the cable, like increasing the tension in the cable, with the help of that, what you will do is, you will get this kind of reduction in the sag or reduction in the deflection. And this is a basic principle that we can understand with this example. Similarly, here with the same kind of example, we'll try to explain the role of eccentricity. So here again, the similar kind of example, you have a UDL, uniformly distributed load. Again, the weight is there, and with the certain amount of eccentricity. So here, we'll go with this eccentricity. Eccentricity E is here, and if we need to reduce this eccentricity, because if we have more eccentricity, we need more depth. So if we need to squeeze, or if we are required to squeeze the depth, we need to reduce this eccentricity. So for this particular amount of force in the cable, and for this particular load is fixed in our case, what we can do is either the span is fixed. What we can do is either we can reduce or increase the eccentricity, or we can reduce or increase the weight or force in the cable. Either we can keep one cable, either we can keep two cable, either we can keep three cables, like that. We can increase the number of cable if we need to increase the force in cable. So here, what we can do is we either we can increase the force in the cable by keeping some more weight over here. So what will happen is, it will try to decrease, or it will try to reduce the eccentricity. So this is a basic key fundamental behind the depth of the PT member, or you can say, we'll try to figure it out physically, or we will try to realize this physically with the help of the other example. This is the example. This is a well-known bridge in California, USA. It's a Golden Gate Bridge, and this is one of the views of, you can say, a very popular view of the same bridge. Now, I would like to highlight the dimensional aspect of this bridge. So these are the dimensional aspects wherein you can see that the clear span, or the pylon to pylon, the span is around 1.28 kilometer. So it's a huge span. And the height of the pylon is around 230 meter. So 230 meter means, it is around 75 story building. So pylon itself is a 75-story building. Now, why to go with this much height of the pylon? So this is required because of this. it needs to generate this kind of eccentricity so that the material and everything can be optimized for this 1.28 kilometer span. So they have fixed it. So this is how this E of 150 meter is being set over there. Now 150 meter, if you want to realize this 150 meter, how much it is? It is equivalent to 50-story building. The eccentricity itself is equivalent to 50-story building, right? So this is how why the pylon height is 230. That is because of this, and that 230 is from mean sea level. It has a maybe it is going beyond the mean sea level in downward. So with this example, we'll be able to understand the significance of the eccentricity and the role of eccentricity in our case. So now, with the same kind of understanding, or kind of similar aspects, we again now focus on to the our beam, whether it is a beam or slab. So in our case, what happens is we are not getting much eccentricity because of the thickness requirement or thickness constraints. The client, either it is an architect or it is a consultant or it is a uh, you can say developer, all wants thinner elements, the thickness of the slab, thickness of the or depth of the beam, wanted to be as minimum as possible so that they get a benefit of working height or overall height of the structure. So here, we need to play with this eccentricity. We need to optimize the eccentricity such that everything like the material consumption or the force in the cable should not be too high, as well as the either the depth of the member it should not be too high. So we need to get balance between both the things with the help of this eccentricity as well as force in the cable. So now this is the overall picture, wherein you have a precompression P by A, then weight balancing effects. So now combining all the effects, this is a design stress. Because of this weight, there will be a design stress created on this particular beam. So that is nothing but compression at the top, tension at the bottom. Then this is the precompression effect, and then this is the load balancing effect, which will be almost reversal. Then almost getting you can say in reverse direction to this, nullifying this both the things. The design stresses will and load balancing will be in reverse nature. And then the overall scenario would be something like this. Here, it would be more of C and less of T, right? As we know, T is actually we are watching out in RCC structures. The T should be as minimum as possible. C also should be as minimum as possible. But what happens is our concrete is good enough in resisting the C, because if I see that say for example we have a third M30 grade of concrete, that is 30 Newton per mm square at 28 days strength of concrete. Now the equivalent tensile strength of that will be hardly around 3 Newton per mm square, 3 to 4 Newton per mm square, right? So where the 30 Newton per mm square and where is the 3 Newton per mm? So it's almost 1/10 of the ratio, right? So this is how actually C will not be that much painful, but T is very much painful. And in resistant T, what we are doing is we are using the reinforcement. So in addition to reinforcement, we can use the PT as a reinforcement also to reduce this T. That is one thing. Second thing is, by if the T is increased or tension is increased, what happens is, you are actually, entering into the durability aspects, because, when the T increases to certain extent, what happens is, concrete will start crack. And if the crack is beyond the permissible limit, what will happen is, the crack will reach to the reinforcement. and reinforcement will be exposed, and by virtue of time and by virtue of this exposure, the steel will start corroding, or corrosion will start occur in the reinforcement as in due course of time, and it will actually harm the durability aspects. So we need to watch out this T to make sure that the structure or the member should be durable enough to in the serviceability lifespan of the building. These are the pre-stressing systems. The one of them is pre-tensioning systems, and the other one is known as post-tensioning systems. Now, in pre-tensioning system, what happens is we are stressing, or the cables are being stressed before casting of the concrete. So that is what is the meaning of the pre-tensioning. We are tensioning the cable before concrete is actually being cast. The second one is known as post-tensioning systems. In post-tensioning systems, what we are generally doing is, we are casting the member first, then there is a cable inside, and then we are stressing the cable. So, we are stressing after casting. That is what is the meaning of the post-tensioning systems. Now, in post-tensioning systems, there are two systems. One of them is known as grouted PT system, or it is also known as bonded PT system. The other one is known as unbonded PT system, or you can say monostrain PT system. So we are into the last one segment, that is unbonded PT systems. We brought this system in India in 2006, and so till now, we have completed more than 1,800 projects with this system, and this is what is our history of this company PTSI. So to give the brief description or introduction about this technology is, it will look like this. This is an icon. So there are certain advantages. You can go through our website for those advantages and limitations as well, because limitations is also in the positive side. We need higher grade of concrete, and a better quality concrete is required. The pouring, and we need to restrict the water cement ratio so that everything is actually in good shape. These are some cost benefit ratios as PT versus RCC. This is also there in our website. You can refer this at your leisure. You can visit our website. It's ptsindia.net. Regarding the brief history, coming to this, how it has evolved and how the advancement has been actually carried forward to this particular system is it was first patented by issued to the PH Jackson of San Francisco in 1886. Then in 1928, the Fressinet has started playing with this, and with the help of the high strength wire and concrete, we started with this fundamentals and applications. And the same guy Fressinet has developed the spatial jacks and anchoring cones in 1939. After that, there was a black chapter of our Earth, that is nothing but the World War II. So in World War II, actually, everything was being disturbed, or you can say damaged to a large extent. All the infrastructures, buildings, bridges have been damaged, and after the post-World War scenario was, now everything need to be repaired or restructured or re-strengthening or retrofitted. Right. So in those on those days, actually, the material part was also being wasted in the World War in carry out the World War II, all the wars. So material part was also on scarcity side. It was all scarce. The material was also not available. So with this consideration, then people came to know that this PT or post tensioning or pre-stressing will require less material. So again, the PT came in picture. So then, 1949-50, there was a first bridge known as Walnut Lane Bridge in Philadelphia. That was the first bridge in Prestressing in USA. Then in 1952, first building in Colorado, that was a cold storage warehouse. And in 1960s, first use of this technology in nuclear containment. Then there was a development in 1970 regarding the metallurgical aspects and the technique of casting and achieving the ductility, that is known as ductile casting, has been developed. And because of that, that helps us in developing the better anchorages, better, you can say, efficient anchorages. And then in 1976, there was a formation of PTI, Post Tensioning Institute. And actually, this is a governing, or you can say regulatory body, or they are the deciding factors in across the world regarding this post tensioning. And they have developed the specifications and what to do, what not to do, and everything. So these are the state of the art developments. To sum up all the history, the first one is the specification being developed by the PTI, then the system of extruding plastic sheathing around the grease and strand was developed. So whatever you see right now, the horizontal member is a cable, and you can see the blue color is the sheathing, the yellow color is the grease, and the dark color is our cable material, or you can say the strand. So this extrusion process, this is being actually manufactured by this extruding process. And the ductile iron casting in metallurgical aspects that develops our encourages to a good and efficient way and share. Then there was a concept of weight balancing in analysis and design, as we discussed with the T-Wiling. A bended uniform layout for two-way slab systems. We'll see this in one of the slides, how it helps and how it makes the construction faster and easier. Then computers for analysis and design. So we get all the things quicker with the help of this quantum computer. And now we have the encapsulated unbonded PT system that is excellent over the corrosion related issues. So now we are using the encapsulated unbonded PT system everywhere. So this is the nuts and bolts of the unbonded PT system. There is a cable, you can see the cable here, right? This is a sheathing, grease, and then the metal part, or you can say strand part. This is the anchor plate. You can see it is all encapsulated. Everything is the material or metal part is all covered with the protective layer. There is a wedges, pocket form. These are the nuts and bolts to achieve the force applied and force locked in the member. You can see this how it is composed. You can see there is a cable inside this anchorages, and then the wedges are applied at this to lock the cable, and after locking, the grease cap is applied to this, so it covers everything. So this is how everything is protected actually. Here is the structure of the cable. You can see the cross section. There are seven wires, and the nominal diameter of this can be 12.7, 15.2, 15.7, like that. Okay. And there is a grease over this. So grease has a two purpose. One of them is to allow the movement inside the concrete while stressing. Right? That is first purpose. The other purpose is to protect the cable, because grease has a property of protection the cable against corrosion. So this grease is anti-corrosive grease. And then there is a HTP sheathing over that. So sheathing also has two purposes. One of them is to allow the movement. The second one is to protect the cable. Now here, the grease will reduce the friction between the HDP sheathing and HT strand while stressing. This is a schematic layout of the system. You can say that this portion, the you can say far end portion, is already being installed, already been cast, and now it is time to stress that part. Okay. So here you can see that the broken part. It's a part of anchorages, and you are reaching. You are first remove the pocket former. You are applying the wedges, and then you can stress the cable, and then you can do the next activities. Here the beauty of this is you can have this pour. This is first pour, this is second pour. So this is a construction joint over there. You can keep the anchorages and you can stress this part first. After stressing, your cable is being continued in the second pour. You can rearrange everything here. You can fix the steel and everything, and then again you can cast this. Again you can stress here, and you can move forward. So this way also you can have a you can keep the same cable from this end to that end. You have a single cable, so it has a more integrity aspects, because the cable length, the one spool, one coil of the cable is having a length around 3 kilometers. So you'll have a seamless reinforcement throughout the your one end to other end of your building with this help of this kind of technology. These are some of the images from the site. You can see the anchorages. You can see the cable is taken out from this side. You can see the yellow part, that is a grease. This cable is taken out for stressing, so that we can grab the cable and we can stress that cable. This is the image from the inner side where the casting is to be done. So this is the casting part, where you can see the laying of the cable. You can have a group of cable being spreaded when it is reaching to the end, so that each and every cable has its own anchorages. So the stress distribution is also even in the concrete. Here you can see that this is a flat slab actually, and this is a column. Then again here column, like that. So here you can see that the cables are at the top profile, because the tension will be at the top when you have a support, and as you go towards the midspan, the cable is again dragging down, dropping down, and it will achieve the bottom part. So there will be tension at the bottom, so it is required at the bottom. Likewise, you can have a cable profile based on the design requirement. And this is the image of once everything is done, then you can say that this dark portion is nothing but the cable were there, and then they were stressed, and now they were cut, and now it is about to patch. So these are the patched, you can say. Everything is patched inside, so nothing is seen outside actually. Nothing is taken out. So here you can see again the kind of flat slab scheme, wherein the cables are being laid. You can see some of the cables are being laid from this and this span to the next span. Here this span is very short, but this span is very low, very large. So we need extra cable here. So we can provide the extra cable like this. So these are the prefixed end, and the other end we are stressing from the other end. Here you can see how the flexible cables are. You can see the cables are being looped. You can see the group of cable are being looped from the one end to the other end again. This can be done where we are not getting the stressing from the other end. We can go with such kind of arrangements. This shows the flexibility, how flexibility is the system. So let me go towards the application in residential building. This is a novel application known as flat plate scheme. And here you can see that the blue line is the slab line, whereas this kind of dark elements are nothing but the columns and structural walls. You can say there are structural walls here. There are very few beams here. There is a beam here like that. There can be a beam somewhere else also, but not in the interior part. Interior part is all flat, you can say. It has only column and slab connections in interior part. So this has been achieved with the help of this kind of schematic layout of the cables, wherein in vertical direction all the cables are being distributed, and in horizontal direction you can see that all the cables are being grouped together. So this is known as banded and uniform laying out, right? This is the image of the same kind of scheme, wherein the band of cable or group of cable is going in this direction, and the distributed cables are running in the other direction, orthogonal to each other. Right? You can see this distribution cable is having high point here, again low point, like that. You can see high point here, low point. And for banded cable, the high point is here and it will be somewhere here. So this is how the flat scheme look like. There will not be any obstruction between slab and column. Then you can get the clear 10 feet height. There can be another kind of scheme that is known as flat slab with column drop panel, wherein uh, the span could be maybe around 8 to 10 to 12 meter, right? And then at the column perimeter, you will get a drop panel. So drop panel is nothing but the thickening of the slab over there. The slab thickness could be more than the overall thickness of the slab in the drop panel zone. So these are the drop panel zones. Here what happens is you are getting the support, the slab is directly supported on the column, so there would be punching actions. So to mitigate the punching action, we need local thickness over there of the slab. Secondly is there will be a peak of negative bending moment over there at the column, and it will be shooting like exponentially over there. So to take care of that, the span or extent of the this drop panel is being used, and this is how we can have a larger expense of the drop panels to take care of those kind of negative stresses. You can see this is a flat slab wherein drop panels are there. You can see this is a drop panel portion. This is a column. Here also there is a drop panel portion at the column. After casting, after removing the shuttering, you can visualize the drop panels like this. These are the drop panels. You can see them, and this is a flat slab. There is no beam column to column. It's all drop panel and slab. So it is good for laying out the services that is suspended below this floor, or you can say below this ceiling. So there can be fire lines, there can be water line, there can be HVAC lines passing through electrical lines. So there will be a jungle of services that is suspended from this floor, and if it is a flat slab, you can run the services in both the directions without any obstruction. This is a flat scheme in commercial. You can see the span was around 9.5 meter by 9.5 meter, and you can see that very few columns are only resting on a slab, but many of the critical columns are being actually bound by the beam framing, right? But this is also achievable, and you can see that how the serviceability aspects has been enhanced with this little bit modification. This is a commercial building. This is also an interesting building wherein the column to column span, this span was more and this span was less. Right. So what we proposed is on the span, the larger span portion, we proposed wide shallow beams, and this is how we reduced the slab thickness, and this was actually being loaded by the client, and the project was initiated with this kind of philosophy. Interesting project is beams with the slab. Here, actually, the client approached us with the columns here. There were columns in the middle part of this. Let me check if I can pointer option. Yeah. So there were a column here, here, here. So at the middle portion of this, there were column in the initial design, and they were having the beam depth as per this column, right? So they didn't have any issue with the depth of the beam. So what we did is, we tried with the we tried to eliminate these columns, and we tried to match up the depth, same depth, and try to achieve that. So it was successfully being done with this, and the client was happy to get rid of this middle column. This is known as ribbed beam with the slab. This is generally loved by the industrial people, wherein you can have a more span here. This span is more than the lesser span or lesser span here, and here the column to column distance, you can say, is more, but here the column to column distance is less here. So with this kind of arrangement of the column, this with the slab was a beautiful option for them, and they can have a circulation in this direction. They can have anything passing through this. Will have a less headroom issues. Actually, the headroom is good enough to pass through everything over there. So the span, or this larger span, is around 20 meter. This was a 16-meter span, and this was a 12-meter span. And we gave him the option of keeping the PT beams in the larger span direction. So this is the photograph of the same project. It is nothing but the workshop for Volvo Eicher in Pithampur in MP, in GIDC over there. It has been completed in 2010, and this is the floor. This part is the PT floor. Then there is a roof. So roof is lighter, but this floor is being designed with heavy load, actually, because here the truck and all the locomotive kind of assemblies were being actually assembled in this particular floor. This is also a very nice scheme for one of the hall in Jaipur. There are 8 columns total. 4 are at the corners. These are 4 columns at the corners, and then 4 columns are at the edges. You can see that these are the 4 columns at the edges. So here, client wanted to have no column inside this. There is no column inside, only a perimeter, and only 8 columns. And the span from this column to that column is around 120 feet. And from this column to this column, it is around 124 feet. Just a second. So here what happens is, the depth of the beam was coming huge in RCC. And because of that, actually this is for Satsang Hall in the Govindavji Temple near Jaipur, in Jaipur. It's near the Govindavji Temple. It's in campus of Govindavji Temple. This is actually just nearby the Hawa Mahal. So they wanted to get the top of this should not be more than the top of the temple. So that was a height restriction of overall building. So they approached us that if we can reduce the depth and we can match up the height of the building restriction with the LVA PT. So then we gave them the proposal, and it worked, and now it is all being constructed in 2009. The loading on this is huge. It's like a loading of the commercial mall, that is 500 kg per meter cube, and 150 meter kg per meter cube is the floor finish, like that. Production, I am audible?
Yes, sir.
Okay. Yeah. Okay. So this is the building after construction. You can see that the grid kind of or waffle kind of arrangement was there. Beams are in both the directions, and the depth of the beam was around 54 inches, but it was matching up their height restrictions. It is being constructed in 2009 and working well in the Jaipur. To add on this project, this has won Guinness World Record on those days, bearing the largest roof, largest flat roof in the world. So this is one of them in Guinness World Record. Earthquake and unbonded PT system. Let's do some little bit on that part, the theoretical part. Okay. So this is generally the bending moment we get in when we have a portal kind of thing, and the UDL is acting on the beam, and the bending moment diagram, the negative bending moment at the support and positive bending moment at the midspan. This is generally this kind of profile is there for gravity forces or gravity actions, that is vertical downward. When there is a sway or horizontal thrust from the either of the end, the bending moment diagram will have this kind of nature, right? And when the thrust, or you can say reversal action, is again there, because building, once it sways in the direction, by virtue of its own stiffness and geometry, and it's can say because this motion, the horizontal, it is not actually tied up above the ground. It is only tied at the ground. So there will be oscillation of the building once it is having a thrust in either of the direction. So this would be the bending moment diagram as far as lateral forces are concerned, and these are the bending moment diagram as far as the gravity forces are concerned. So here the beauty is these are acting majoritarily on the beam column junction, right? And these are majoritarily working on beam column junction as well as the midspan, right? And this midspan portion is creating the deflection issues. So we'll try to resolve this and we try to accommodate this kind of lateral forces in PT. Actually, PT is not meant for the lateral forces. PT is meant for permanent forces. Now, if we see what are the permanent forces in our system, the one of the permanent forces is the self-weight of the structure. And if you see the self-weight of structure, if you compare the self-weight of structure with the imposed loads, the self-weight of structure itself is more than 60%, 70% of total load, right? And when we are discussing about the large span, again this goes on a higher side, because large span requires more concrete and ultimately the more self-weight. So the self-weight is a more governing force, and that self-weight in gravity force generally in large span structures more than 40, 50, 60 feet span of beam, in that case generally gravity governs with respect to lateral. Lateral will not govern the design, gravity governs in that case if the beam size is large. Now superimposing all the actions, all the bending moments like this, what we are getting is this kind of envelope is actually being generated. So dark red line, a dark black line, you can see that this is the envelope portion. So here you have to provide the part of gravity, or you can say self-weight part, or a little bit of other dead load part is being taken care by the cables or pre-stressing, and other transient load like earthquake and live load can be taken care by the passive reinforcement. That is nothing but the non-pre-stress reinforcement, or you can say HYSD or Fe415 reinforcements. So here, the gravity reinforcement is there, whether it is PT or some HYSD is also there, and plus extra reinforcement is required to take care of this kind of demands that is generated because of the lateral actions. Here, generally, there will not be any demand with respect to lateral. Let us discuss a little bit about the ductility part. Ductility can be achieved effectively by this kind of arrangements. Let us study this diagram or graph of the stress versus strain of the concrete. So here, if the plain concrete is there, then the stress strain diagram will be like this. This is the stress strain diagram for the plain concrete. But if we are confining the concrete, then this would be the stress strain diagram. So by confining the concrete, there is a considerable enhancement in the ductility. Right? You can see the ductility part. This will guide us about the ductility part. Right? So here the ductility is extremely, you can say, enhanced with the help of this confinement. So we can confine either by the longitudinal steel. These are longitudinal steels. You can confine with this help, and effectively more onto that is by providing the transverse reinforcement. That is nothing but the stirrups. So by keeping enough stirrup and longitudinal reinforcement, you will be able to achieve the required ductility in PT element as well. Regarding stiffness factor, in IS 1893 part 1 2016, this is the stiffness factor that is being asked for the analysis of building for earthquakes and wind and all the things. So here in 70% of the I gross of column to be considered, and 35% of I gross of beams to be considered. Now here 70% of column is okay, because column is already having the pre-stressing actions on that, and it is confined, and pre-compression is already there by virtue of the self-weight, and so actually it is already compressed, right? Whereas in case of beams, in RC beams, generally they are not having that kind of mechanism of pre-compression. So that is why code suggested to go with 35%, or you can say 0.35 of I gross. So it is coming very low actually. And because of this, what happens is, your size of the beam and reinforcement in the beam is huge. This is regarding the IS developments actually, but in ASC 4117, actually they have given the similar kind of table with the stiffness values. You can see that for the non-pre-stress beam, it is similar to our case, that is 0.3, right? But beams with pre-stressing, they suggest to go with the 100% gross value, right? 1 times that IG. So there are certain benefits of having this pre-stressing in your beams. But still, the code code is silent about this, so we cannot take this example in our case, in Indian case. But yes, across the worldwide or in ASC, this has been put up. So there are chances that we can foresee that some upgradation, some kind of improvements will be there in our code as well. some extracts from the literature. This is a PTA technical notes wherein they are emphasis on the inelastic strengths that is being developed in bonded tendons. This is regarding unbonded. So unbonded is behaving better than the bonded because of this inelastic strengths develops in the bonded, whereas this kind of inelastic strengths are not being developed in the unbonded tendon. Actually, in unbonded tendons, it hardly exceeds the elastic strengths. It is not going beyond the elastic strengths. It is well within the elastic strength limits in general case. Because of that, what happens is it can retain its initial stiffness. So because it is not crossing the elastic limit, it can retain its initial status. This is a very good literature, earthquake performance of unbonded post-tension buildings in 1990s. It was being carried out after the Loma Prieta earthquake in 1989 in California. The intensity was 7.1 and the epicenter was near San Francisco. So in nearby area of San Francisco, over 200 PT buildings were surveyed, and with various kind of different structural configurations like PT flat plates, slabs, one-way slabs, beams, transfer girders, transfer floors, etc. And the observation was such that PT in all categories of the structural members examined appear to have performed well during the seismic motion. No sign of blowouts, rupture of strands, cracking, or dislodging of the anchorages were actually found. So this is a very good case study. We can share this if it is needed. We have this document. In post-tensioning manual, that is the recent manual 6th edition, they have emphasized on the behavior. That is, the unbonded behaves more of elastically. It doesn't enter into the plastic zone, or it doesn't enter into an elastic zone. So it rarely exceeds the elastic limit. This is the statement taken directly from this 6th edition. It is in chapter 8. Now the practical aspects I'll discussing about installation in large PT beam. So this is a large span PT beam. You can say that the span from this end to this end is around 80 feet, and you can see that the sides are not being closed till the installation of the cable is completed. Once the installation of the cable is completed, then the sides will be formed, will be fixed up, and then the casting will be carried out. This is extra large depth beam, you can say. I would not say it is a beam, but it is a girder actually. So this is how the installation of a large depth girder can be carried out. You can see the blue element is nothing but the cable, and you can see the profile of the cable. Let me show you the in depth of this. So now the green color lines are there. So this green color lines are, this is a base of beam. So there are columns below this. So the columns are being displayed by this yellow color, and there are floating columns on this particular beam, and it has a huge load on this coming to this, because below this there is a large span requirement of hotel. It is for Hyatt Palace in Baroda. This is a project of Hyatt Palace in Baroda, and they wanted to have a large span below this particular floor, and hotel rooms will not require large spans. So there are columns. So there is a you can say mismatch of the column location. So that is why this is a transfer floor, wherein this beam will take care of the floating columns. You can see the end of the beam and the arrangement of the cables, and the live end, you can say, from where the stressing would be carried out. Actually, this beam is a kind of I section, wherein the bottom flange is nothing but the floor itself, and the top part is to be constructed, or top part is to be poured afterwards. So this is a service floor actually. So this beam is bridging both the floors. Now after casting, after stressing, you can see that both the floors, the top and bottom, and this is the bridge, and it is taking care of the floating columns. Some interesting cases we came across after having this much projects. Here, this was a project in Mumbai, and as you see, the span is large. Like it was around 60-70 feet. Now, after construction of several floors, then there was a change that is actually being forced by the municipal committee, and the client has to trim this end 800 mm inside, or 500 mm inside, sorry. So after construction, the cable ends are there, and the force is being transferred through those ends. So it is a very critical situation for the client. But we did this kind of job as per the requirement of the client, and we trained this, and I'll show you the photographs of the same. So here the building boundary was somewhere here, and now it would be somewhere here, right? So this part is being actually the concrete is being removed, and again the anchorages are being fixed on this area and stress those things, and you can see the other angle. This is the existing, and now it is trimmed to this end. Opening in PT slab. So opening means I'm approaching with the lesser diameter of the opening. So these are the opening that is actually being initiated after construction, after casting of the and after stressing. So here you can see that stressing. You can see the layout of the cable. From the layout of cable, those markings were also being there. So to guide us that where are the cables. And based on that, we can always allow this kind of core cutting for the plumbing and all other services. So here you can see there are a lot many services if you can just look after. So here there are a couple of services, huge group of services, again here, again here. So this kind of services can be laid up afterwards also. It's preferred to provide this kind of sleeves before casting, but if it is not done or planned before casting, still it can be accommodated afterwards with a proper caution. These are the small openings around 2 feet, you can say, in PT slab, and the cable could be somewhere like this. Cable can go, and in between the two cables we can have this kind of opening. Then a large cutout. Say for example, the building, the column to column here, the distance was around 60 feet, and this is around 15 feet, like that. Here you can see that they wanted to have this kind of cutout in the PT slab. So, and that was in couple of floors, not in one floor. So we tried to remove the concrete over there, this is a actually the blue color hedge zone is nothing but the proposed cutout part. So we need to break the concrete little more to take care of the anchorages and fixing those things. So that is why little more part is broken, and then the concrete. And then here you can see that the cables are being these are the cables actually, and then the anchorage treatment is being fixed over here. So there is a slab hidden beam, and across from this hidden beam, the anchorages are being fixed. And then meanwhile, we also washed out the condition of the cable. So this has been actually initiated after 1.5 year of the construction. So still the cable is intact, good condition. Grease is also working well. So here after this, you can see after this the concrete is being cast here. So after casting, you can see that part is here. So this is that part. After casting, the cables are being taken out. So from there, we can stress the cable. Here, there was a requirement of adding a support line. So we need to give a beam over here. So this is added beam in the existing structure, and then this part is being actually cast afterwards. So now you can see that after that these are the cutout. This is a cutout in the floor, and this is the cutout in the next floor. So then we also came across one project wherein a building is already being constructed. Mall building was constructed, and then half part of the mall was to be demolished because the client changed his mind, and now he wanted to have some other scheme on that half part of the campus. So sorry, that is the next case. This is a demolition of one of the floors. So here terrace is being demolished. You can see that because of the height restrictions. So this was a PT floor, but now it is demolished, and you can see from the top, you can see the cables are being exposed in the broken part. So this is possible. Now the demolition of PT floor. So this is a mall wherein the client wanted to. This is a plan of the mall. I am just discussing the schematic part first. This part need to be demolished. So we worked out the contact points wherein we need to treat and where we need to treat our knife. This is how it is cut, and the part is demolished. And the new scheme is being developed here. Now I'll show you the photographs of the same. This is a Google photograph. You can see this is a project in Surat, and you can see this is the project. Now it is being cut. There is a bridge here, and I'll show you the photograph of the bridge also. And after cutting, you can see that this part actually this part is land acquired by the same client. So there is a scheme over here, new scheme. So you can see the new scheme here. This is entirely a new scheme over here. So I'll show you the photographs. You can see the photographs. This bridge portion, right? It was like this, and now it is being demolished. Part of demolition here, part of demolition of the slab here, like that. You can see that it was connected here. This part was connected. Now it is demolished. Again here also there was a connection, so it was all demolished. Here also demolished. You can see some part here demolished. While demolition also, this is being like I think after 2.5 years of construction, this was being demolished. So after while demolition, we washed out the cable. Still, cable is in good condition. The grease is also a good condition. You can see that the grease patches are there, so grease is working good. Retrofitting and re-strengthening of the project with the help of this kind of system, that is unbonded monostrand PT system. Here, this is an interesting part. Generally, what happens is, in case of PT slab or maybe it is RCC, but still, we need to have a limitation in the casting. So because of that, we can cast a limited portion if the area is huge. So we need to define the pores, pore 1, pore 2, pore 3, like that. So here actually this is a pore strip, need to be cast afterwards, after stressing of the cable, everything is done, then this need to be poured, and after casting this, after having a strength gain in this pore strip, then and then the shuttering or reshoring or shoring or supports below this floor need to be removed. But in this case, what happens is, before pouring, before casting here, the contractor, the persons of the contractor has removed the supports in this zone, below this. So now you can see that what happens is, this is a cutout. There is no continuity between this column and this column. And this is now acting as a cantilever, and it is not being designed for this cantilever action. So there was a crack formation in this direction. So this is a crack formation. There is a crack, and there was a sag in this portion. So here, the span from here to here was around 8 meter, you can say. So it is huge cantilever, and it was not designed as a cantilever. So this kind of mishap can happen because of this premature removal of the supports, if the support removal is not being treated as per the requirement of design. So here also this kind of retrofitting or re-strengthening cases we handled. One interesting case is regarding the steel girder. This was a PEB girder, pre-engineered girder. The black is the girder, like this. So, and these are the other secondary girders resting on this primary girder. Now here it was observed that there is a sagging in the girder. This is a tracing of the bottom of the girder. You can see both the red lines is nothing but the bottom of the girder, and where it tries to match, that is the mid span. This is the mid span of the girder. This is support 1, then this is the support 2. So if we want to realize this, how much is this? You can have a straight line here. So this is a straight line that should be the undeflected shape or undeflected position of this girder. So this much is the deflected girder of the girder at the mid span. So client wanted to again strengthen this part. So we try to give them proposal with the introduction of the post tensioning cables externally, and try to pull it out and try to strengthen this part. There are few iconic projects we constructed till date. I would like to share those things. This is one of the iconic projects we did in Mumbai, in Lower Parel side. It has a 40-story. It is a 40-story building. So it was one of the top 10 buildings in 2009, 10, 12 in India. And we entered from the 19th floor. So up to 18th floor, it is all RCC. Then actually, we approached them, and client liked our option, and then we started working from 19th to 40th floor. And because of that, they could add 2 more floor on this total height of this building with the help of PT. So additional floors has been constructed because of this PT, because you can save some height at every floor. Say for example, you are saving say 1 feet height at every floor. So at 11th or 12th floor, you will have one more floor like that. This is a very huge project we completed, that is for TCS, Tata Consultancy Services, in Powai area. And this is a phase one. It is a very huge building. Phase two is also similar to this, in nearby this. It is also completed by now, and phase three is also about to complete. This of the same client, Tata Consulting Services. It is a huge project. So you can see that the total area of this particular building is this much. So and it is actually completed in record time. So you can see some YouTube videos from the Hiranandani. You will come to know that now how this construction is being carried out. So Hiranandani is one of the reputed group in the Mumbai. This is an IT park in Mumbai. You can say that there is a podium. This is a podium part, and of 3-4 floors, and then the tower part. All are flat slab schemes, and it is completed in I think 2015-16. This is a commercial complex in Ahmedabad. Here the iconic part is this kind of some inclined shape members. This is also, there is an inclined shape members, some inclined shape here also are there. No doubt this inclined shape is of structural consultants purview, but still there are some actions that need to be taken care by the floors itself. So those are being communicated well with the structural consultant, and we could match up their design requirement in this particular complex or project. This is for Shivalik Group, a well-known group in Ahmedabad. This is one of the recent projects we completed in Ahmedabad. This is also a huge project. You can see that this portion is already being finished, and this is under construction. So this is all one project from here to here. Again, this is the photograph under construction, but now it is all completed, and it is also completed in record time. So this is in Shamal Crossing over there. This building is there. That is known as iconic Shamal. This is an interesting project we did. That is a large amphitheater and auditorium combo. So here what you see is that the top part is nothing but the amphitheater, and the bottom part is the auditorium. The span of this was around 100 feet in both ways. There is no column in the intermediate part. It is all at perimeter. And the iconic part is the imposed loading. So imposed loading was around 1000 kg per square meter. That is 1 ton per square meter. And that was a loading considered in this for this amphitheater part. You can see that some blue color cables. This is highlighted one of the beams. How the beams are being profiled. You can see that there is a crank shape from here. These are the cables. You can see the cables. These are such beams. You can see parallel beams. Here also there are beams. Here also there are beams like that. Again, the photograph from the other angle. You can see the cables. The blue colors are cable, and you can see the crank part of the beam. So it was a huge project. You can see the top part. That is nothing but the large amphitheater part. You can see the steps and everything. You can see the width, and similarly this part is also huge. And this is from the bottom. Now you can see the beauty, right? So this is a huge part. This is also a huge part. It's around 100 feet. One of the projects we completed in 2013 is for the Sandeep Foundation campus, entire campus, almost all the buildings in Nashik. It was an institutional building, and it has classrooms, auditorium, this the library, then the administration room, everything was there. This is an iconic shape constructed in Baroda, corporate of building. You can see the shape of the building. So any shape can be materialized with the help of this PT system. Again, you can see the shape. So this kind of shape also is materialized with the help of this kind of PT system. This is one of the recent building we completed in Baroda. It's for the Linde Engineering. This is a corporate office for the Linde Engineering office. This is the CGI and this is the real photo. Here, this part is actually, below this part there is a parking. So the loading was used to consider for this because there is a lot many level drops are there, undulations are there in the levels, and then there was a garden load on this. All the floors are also in PT. So with this, I would like to go with the question answers. If there are questions, we can go with those questions, and I'll try to